morning everyone. In this video we will continue discussing about these system design decisions. We'll be looking at breaking a system into subsystems. So I'll discuss about what are subsystems, what are layers, and what are partitions. So the first step in system design is to divide the system into pieces. Okay, these pieces are actually called subsystems. These subsystems actually provide you some sort of functionality. So each system is based on some common theme, such as similar functionality, the same physical location, or execution on the same kind of hardware, etc. Okay, so they should be under a common theme. Okay, so it should be based on a common theme. So think about, say, for example, if there is a spaceship computer is there. Okay, this might include subsystems, something like for the life support, navigation, engine control, and running scientific experiments, etc. These sort of things. So that's how the subsystems build. A subsystem is actually a group of classes, associations, operations, and events and constraints that are actually interrelated. So everything which we have discussed in terms of the class model, okay, so all of them actually fit into one of the subsystem. So it is actually a group of all these things, and these things are actually interrelated. A subsystem is usually identified by the services it actually provides. Okay, so a service is actually a group of related functions that actually share some common functions. Okay, so for example, like the file system within the operating system is a subsystem. Okay, management of the file system and everything is actually taken care by that file system. Okay, which is a subsystem. Each subsystem will have a well-defined interface to the rest of the system. Okay, so the interface actually specifies the form of all interactions the subsystem will have, okay, with all other subsystems within the actual complete system. So the subsystem actually the interfaces specifies the form of all interactions and information flow across these subsystem boundaries. But these interfaces do not specify like how it is actually implemented internally. Okay, that is actually taken care within that subsystem. So basically, like the subsystems will be existing independently, and they will have some interfaces using which like they can interact with other subsystems. We'll see examples by the end of the video. So since the subsystems are existing, okay, so you will basically develop, you will split these subsystems, and these things can actually communicate. So the relationship between these two subsystems can be actually based on client server or based on peer-to-peer things. Okay, so a client server relationship, the basic idea is like one of the subsystem acts as a server, okay, another subsystem acts as a client. The client actually calls the server, which does some service for you and replies with a result. Okay, the server subsystem is one, the client subsystem is another one. Okay, in this case, like the client must know the server's interfaces, otherwise it is not required. So the server don't need to exactly know about the interfaces of the client implementation, client subsystem implementation. So that's how like these two subsystems will interact in a client server approach. Alternatively, there can be peer-to-peer relationship between two subsystems. So in this case, like both of them are at equal level. Both the subsystems are at equal level. Each subsystem may call on the other. So subsystem 1 may call on subsystem 2 may call on subsystem 3, and 3 may call on 1, okay, and 2 may also call on 1, okay. In this sort of relationship, a communication from one subsystem to the other need not be followed by an immediate response. Okay, this is something which we should remember. However, when you think in terms of developing systems and then like dividing them into subsystems, okay, a one-way interaction is much easier to build, understand, and change than a two-way interaction. So basically, like look for client-server decompositions wherever possible, rather than the peer-to-peer relationship. So that's about the relationship between two subsystems. So the decomposition, okay, so this is what we are doing. So we are taking a system and you are actually decomposing it into subsystems as part of the system design, and then like you will be developing each and every subsystem. So the decomposition of these subsystems into subsystems may be organized in a sequence of horizontal layers or vertical partitions, okay, or combination of both layers and partitions. So I will discuss about all these things, okay, and then like I will also give you the examples. Let's look at this sort of decomposition. Let us look at first layers. A layered system is an ordered set of different types or layers. Okay. So each layer is built in terms of the ones below it and provides implementation basis for the ones above it. Okay. One of the very well-known layered system which you all should be knowing is about this what you say reference model for network layers. Okay, for networking or TCP/IP. Okay, conceptual layers. You have this physical data link layer, network layer, transport layer, session layer, presentation application layer. Similarly for TCP/IP, okay, network interface, networking layer, so transport layer, application layer. So each layer is built in terms of the ones below it and provides implementation basis for the ones above it. So that means like once you have the implementation for this physical layer, which can be used by the data link layer. The data link layer's implementation is used by the network layer. Okay. And as we have discussed in the previous slides, like there will be interfaces using which like uh, basically you can communicate. Okay. So coming back to this layered discussion in terms of object-oriented system design is concerned, the objects in each layer can be independent. Okay. Of course, often there is a correspondence between the objects in different layers. Okay. And this correspondence basically happens through interfaces, as we have discussed in the previous one. Okay. But one important thing is knowledge in these layers is always one way. Okay. A subsystem knows about the lowest layers below it, but has no knowledge of the layers above it. Okay. So one of the subsystems, say for example, like the transportation layer basically knows about the layers below it. So basically like network. So it may also know about data link layer and physical layer. Okay. But it has no knowledge of the layers above it. It don't know about the session layer. Okay. And a client server relationship exists between these layers. There are two forms of layered architecture. One is the closed architecture. So in the closed architecture, each layer is built only in terms of the immediate lower layer. So that means like it knows about the immediate lower layer, but it will not be knowing about any other layers which are below it. Anyhow, it is not, it has no knowledge about the layers above it. That's very clear. Okay. But in a closed architecture, okay, so it has knowledge only about its immediate lower layer. The other architecture type is like open architecture. A layer can use features of any lower layer to any depth. Okay. Say for example, the TCP/IP layer. So it can basically like the OSA model can any layer can know as deep as possible if it is implemented in terms of this open architecture. Okay. So a layer can use features on any lower layer to any depth. But there are several problems with this one. So these do not observe the principle of information hiding anymore. So literally like every layer is basically exposing its interfaces to every other layer. Okay. The big problem with this one is like if there is any change in one of the subsystems, it will really affect like every other subsystem, every other higher level subsystem. Usually problem statement specifies only the top and bottom layers. Okay, so most often like how do you design these layers? Okay, so usually problem statement basically talks about the top layer, okay, which is the desired system, and the bottom layer that is about the available resources you have. So all these intermediate layers are built as subsystems. Okay, they are actually introduced if there is a huge conceptual gap between these adjoining layers. Okay, so that's how like you will keep on introducing one of layers one after the other. Okay, this is the layered way of dividing a system into subsystems. The other approach is partitioning. The partitions actually vertically divide a system into several independent and weakly coupled subsystems. So each partition provides one kind of service. Okay, think about a computer operating system. You will have the file system, one subsystem. Then there is process control, which is implemented as one subsystem, and virtual memory management will be another subsystem, and device control will be another subsystem. There will be several subsystems which will be existing, and these are actually implemented as partitions. So file system is a partition, process control is a partition, virtual memory management is a partition, device control is a partition. Subsystems may have some knowledge of each other, but avoid major design dependencies. Okay. So in this case, like the communication is in the form of peer-to-peer. Okay, in the partitions. So that's where, like, let us see the difference between partitions and layers. Layers, there will be different layers, and the layers, their level of abstraction can be very different actually across different layers. But partitions divide a system into pieces that have approximately similar level of abstraction. Okay, layers can be, their abstraction levels can be pretty much different. Okay, whereas like partitions will have similar level of abstraction. Layers seriously depend on each other. So usually a client server relationship, okay, through an open or closed architecture, we have already discussed. Closed architecture means like you know about the layer only one below it, okay, below that particular layer. An open architecture, you will be knowing about all the interfaces of all the layers which are below a particular layer. Okay, so in that sense, like layers depend on each other. Partitions are actually peers that are actually independent, okay, mostly independent, are mutually dependent. I mean, like if they are dependent, and then like if they have to communicate, they will have peer-to-peer relationships. Okay, so that's the difference between partitions and layers. Most often, generally, like the systems will have both layers and partitions there. So we can decompose a system into subsystems by combining layers and partitions. Most large systems actually require a mixture of these layers and partitions. Okay. Say, for example, think about an application which is described here. So this one will have, say, for example, at the lowest layer, it has this computer hardware, and then like this operating system, and then like at the next layer, like there can be several partitions. Okay. So user dialog control, okay, will be one partition, okay, of the subsystem, and simulation package another subsystem, and then like the graphics again will have different layers. Okay, say for example pixel graphics, screen graphics, window graphics, and then like the actual application package is at the top level. So this application which is actually developed, the system which is actually designed, okay, has several layers and also partitions. Okay, and this is what is actually identified during the system design. Once you identify these sort of top level subsystems, you should also show their information flow. Okay, the information flow is like how different subsystems are actually communicating. Okay, how the information flow is actually happening. So it can be based on several things. Say for example, there can be a pipeline where, like, say for example, information comes into one of the subsystem, then goes to the next one, then goes to the next one. Alternatively, there can be a star topology where a master subsystem actually controls all the interactions with other subsystems. Okay, so there are different types of this sort of information flow is possible. Okay, once you build these subsystems. So let us look at this ATM subsystem again. Okay, so ATM application which we are developing, I mean which we have been discussing. Okay, so this has three major subsystems. One is the ATM stations. The other one is that like the consortium computer, and then like the bank computers. Okay, there are three major subsystems here. Of course, like each subsystem will have its own classes and all sorts of things. Okay, so which we have already discussed, classes, associations, and everything. It will have its own, more or less, like it is complete application. Okay, it is a subsystem. So in this ATM case, like these three subsystems, okay, so the ATM station consortium and then like bank computers, they are actually communicating, or like information flow is happening through this star topology. Okay, so the consortium computer actually communicates with all the ATMs and all the bank computers. So this is actually acting as a master. So this subsystem is actually acting as a master. So the user is actually interacting with the ATM, okay, through the user interface. The ATM is actually communicating with the consortium, and consortium computer in terms is communicating with the bank computers. Okay, there are multiple ATMs and multiple bank computers, but there is one consortium computer. This consortium computer actually uses this station code to basically distinguish the communication lines for each and every ATM station, and it will have this sort of bank code for distinguishing the communication between the consulting computer and then like different bank computers. Okay, so this is how like you will be actually during the system design, you will be dividing a system into several subsystems and how they actually communicate. Okay, how the information flow is actually happening. So regarding the references are concerned, we are still in chapter 14 of this object-oriented modeling and design with UML. Okay, Michael Blaha and James Rimbaugh. Okay, thank you very much for your attention.